This is ego-utilitarianism. This video is just about a cool coin problem I saw on a video. I just wanted to present my solution to what the professor was posing to the little kid in there. So let me play that, the audio at least.
Question. So we've got a row of coins, lots of coins, 1,000 coins.
That's a lot of
And
points.
they're all heads up.
Okay.
Numbered 1, 2, up to 1,000. And I go along, and every second coin I turn over. So the second, the fourth, the sixth, I turn them all over back to tails.
Yeah.
Okay. Then I take every third coin, so coins number 3, 6, 9, and so on,
Yeah.
and turn all them over. So I guess coin number 6 is now back to being heads.
Yeah.
And so on, and so on, and so on, until eventually I turn over every 1,000th coin, i.e. the last coin. Here's the question. Which coins are heads up?
The prime numbers,
Why is that?
because they aren't multiples of.
Okay, so he presented the coin problem where you're flipping coins, starting face up. So obviously, if a coin's flipped twice, then it's heads up. So we're looking for all the coins that were flipped an even amount of times. And so if you notice in the problem, a coin is flipped every time you consider a factor of it, right? So you start by flipping every second coin. So every number that has 2 as a factor will be flipped. When you get to every third coin, you're going to flip every number that has 3 as a factor. And so if you take these two into account, right, you're looking for the numbers with an even amount of factors above 1 or an odd amount of natural number factors, right? So you're looking, you're looking for the numbers with an odd amount of natural number factors that includes 1. So again, that's an odd amount of the numbers with an odd amount of factors 1 or higher. And so I think that was that's what the professor was looking for in that case. But you can actually further define the set and come up with a more specific answer. I think the professor was actually looking for, if he was truly a super genius, he actually guessed the right answer. He said perfect squares later, but this is not somewhat intuitive. I mean, empirically, you can start flipping coins, or you can work it out on a piece of paper, flip the first. You can keep doing it up to a certain point, but 1,000 coins is just, it'll take you the better part of a day to empirically test to see that it's all perfect squares. And then you can, I mean, if you want to make it hard, you could increase, you could arbitrarily make the size of the coins you're flipping 1,000,000 or 10,000,000 or infinity, and the case should still be true that it's the perfect squares, because it's incumbent upon whoever's trying to show it's a perfect squares, not just empirically working at the first 49 and seeing that all perfect squares from there work, but the problem is you're not sure that they're the only set that works. There might be another number that's flipped an even amount of times that's not a perfect square. So you have to prove all perfect squares fit this, and you have to prove that the perfect squares are the only set that fits the criteria of having an odd amount of natural number divisors. So I'm going to use some theorems of mathematics. So every number under the fundamental theorem of arithmetic can be decomposed into prime number factorization, right? See, this is a theorem in math called the fundamental theorem of arithmetic, where any whole number, any natural number themselves can be decomposed into a prime number factorization. That means it can be a product of prime numbers with integer powers, right? So if first I have to prove all squares have an odd number of factors, right? So you can take any number, any natural number, and decompose it into its prime factorization. So we'll just call it A1, A2. So these are the prime factors, A3, dot, 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 and so on and so forth, all the way to A to the N. And then it'll have I, J, K, say, I don't know, Z. So the prime number factorization with its powers, that means, so in order to count the factors, it's actually just counting, right? I contend it's gonna be all these exponents plus 1 because of 0, right? So when you're counting from 0 to n, there's actually n plus 1, there's n plus 1 natural numbers in that sequence. So again, if you're counting 0 to 3, it's 0, 1, 2, 3, 4. So there's 4 there. And it's in the general case, it's n plus 1 when you're considering it n as a natural number. So I can so a perfect square intuitively will have an in the prime factorization. All the exponents of the prime factorization of the prime factors will be even, obviously, because it has to be divisible by 2. So they all have to be even. So if all of these are even, right? To count the number of factors, you just actually multiply all these even numbers plus 1. So you're gonna get a product of, so when you're counting the number of factors, you just multiply the exponents plus 1. So you're gonna get even. So it's gonna be 2n plus 1. So the product of any odd string of odd numbers will be odd itself, right? And therefore, since that product is odd, then therefore the number of factors is odd. So I've just shown here that all perfect squares have an odd number of factors, including 1, right? And then so now I have to show that it's the only set, right? So that means the contrapositive is, if it's not even, then it has an even amount of factors, and that will prove that the perfect squares is the only set that fits this criteria. So that means only perfect squares will be heads up in the coin problem. Okay, so that means, so if we have, again, so if n is not a perfect square, equivalently you can show, I'm not going to do it here, but there's at least one odd exponent of its prime factorization, right? So again, if the perfect squares all have even exponents in the prime factorization, that means the negation of that, if it's not a perfect square, then at least one of the exponents is odd. A2, A3, all the way to A to the N, dot, 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 A to the N. And you have I, J, K, all the way to the Z. So again, one of these, at least one of them, right? And so when you have a product, so if all of these except for 1 is odd, that means all of those except for 1 is even. So you'll have even, and at least 1 odd. And when you get at least 1 odd, that means when you add 1 to them, because you have to account for 0 again, because if all exponents are 0, that's the factor of 1 counted, right? So again, if one of them is odd, that means you have, when you're counting the number of factors, multiplying all the exponents at plus 1, you're going to get odd times odd times odd. And then guess what? That at least one odd factor becomes even, and therefore you're multiplying by an even number. And any product of integers that contains at least one even becomes even itself, because the 2 just factors out, right? So I've just shown that if it's not perfect square, then it doesn't have an odd number of factors, including one, that are that are natural numbers, right? Natural number of factors that are greater than one. Natural number of factors. It has an odd number of natural number of factors, and therefore I've just shown that the perfect squares is the only set that solves this problem. I just felt that this was bored and just wanted to make a video, so I hope this is interesting to somebody.